This is Jack Jackson with part 15 of our lectures on discrete probability. For a while now, we've been lecturing on some different types of distribution, and we're going to look at one more today. This is the hypergeometric distribution. So, for example, we've been looking at the geometric and the binomial distribution, and that hypergeometric is kind of similar to these, especially similar to the binomial distribution. In fact, we notice we'll just change one little thing about the binomial distribution and it'll turn it into the hypergeometric. So let's review what we do know about the geometric and binomial before we go on, and then later on I'll compare and contrast the binomial and the hypergeometric at the end here. So the geometric distribution and the binomial distribution, both cases we're doing some independent Bernoulli trials, so the probability of success is P every time we do a trial. Very important. That's one thing they have in common. The difference between the two is what we're counting is completely different in the two. In the geometric distribution, we know we're going to have one success. What we don't know is how long it's going to take us to get that success. So X, the random variable, counts how many trials we get until we get that first success. We know one success. We count how many, this unknown number of times it takes us to get that first success. In contrast, a binomial distribution, we know how many trials in the sample size or the number of trials is a fixed number. What we don't know is how many successes we're going to get, and that's what is the random variable X. So again, geometric distribution, we know it's one success, we count how many times it takes us to get there. Count the trials. Binomial, we know the trials, that's in, we count the number of successes, which is unknown. So since the hypergeometric is very similar to the binomial distribution, we're going to review a binomial distribution example. In fact, this example is very much like the last example done in the binomial lecture, which probably you just watched not too long ago. Only one number has been changed here, so it's really the same thing. So we have an urn with 10 balls in it. 6 of them are black, and the other 4 some other color. Let's say they're red. And we randomly draw out one ball, and note its color, replace it, then draw a second ball, replace it, draw a third, replace it, draw a fourth ball, replacing the ball each time. This is the part we're going to change for geometric in a minute. So in a binomial distribution, it's done with replacement. X counts the number of black balls, so we're going to consider that a success. And this is an example that you should know how to do by now. So let's let you try to finish this up. It may take you a couple minutes here to do this, but let's go ahead and make a tree diagram, the formula, the table, and the graph of the PDF. Work this one all out completely for this example. Press pause now. Okay, so now that you're back, you should have worked through this. Notice, first of all, that it is a binomial distribution because the probability of success P is 6/10 or 0.6 every time. Of course, that makes Q 0.4. Probability of failure. The fixed number of trials, 4 balls that we're drawing out, they're done with replacement, so that's what makes the probability the same every time. That's what makes the trials independent. And X is counting the number of black balls, the number of successes, so this is in fact a random variable that is binomial. This is what the tree looks like, exactly like the tree from last time on the end of the binomial distribution. We've gone 4 layers deep, and this time the numbers are slightly different though because the probability of success is 0.6 and the failure 0.4. Otherwise this tree looks exactly the same as the one we did before, and there's the table as well. There's the binomial distribution. Look at the bars real fast. Notice you've got 2 bars at both 2 and 3 that are quite tall and the same height actually, and then the one at 0 is real short, and then a couple others are kind of in between. Now let's go on to hypergeometric. Suppose that we have an urn with 10 balls in it. 6 of them are black, 4 are red. Exactly the same situation as last time. We're going to draw a ball, see its color, draw another one, and so forth. But this time we're not going to replace the ball. That one little twist, doing it without replacement, means that now the probabilities each time, those conditional probabilities of a success and a failure each time, are dependent on what was drawn the first time. So it's not always 6/10. It is the first time is the 6/10 for a probability of a black ball, but that conditional probability that we draw a black ball the second time depends on whether we condition it on having drawn a black ball the first time, in which case the probability actually goes down from 6/10. Or if we didn't draw a black ball the first time, then that probability of a black ball the second time goes up a little bit, more than 6/10. So the probabilities are changing each time. So these are not independent Bernoulli trials. They are Bernoulli trials, but they're not independent. The probabilities are not the same each time. They depend on what's happened before. So take your tree that you did last time, or actually make a new tree, and formula and table and graph, and see if you can work this one out. This is going to take you a little bit of time to work this out, but it's going to help you out if you try to get some of this worked out on your own. So go ahead and do that now. Press pause. Okay, so here we go. We're going to use some new letters for some of our parameters. We're going to let capital N be the total number of items. In this case, that's the 10 total balls. M is going to be the number of successful items, which in our case is, that we start with at least, that's 6. So N is the initial number of items total. M is the initial number of successful items that we could choose. And lowercase n, notice by the way, uppercase n and lowercase n are two different things here. Lowercase n is the number of items we choose, which is 4. We know what that is. And in fact, we know what we start with. Capital N is 10 and capital M is 6 as well. And then we count X to be the number of successful items. So this tree starts out exactly the same as last time in the sense that each branch has a success and a failure. It's 4 deep. And it even starts out with the probabilities the same, 6/10 and 4/10. But from there, the conditional probabilities are different. So notice if we get a success the first time, we've drawn out one of the 6 black balls. So the total number of balls goes down 1 to 9, and the total number of black balls goes down to 5. The number of red balls is still 4, so the probability of a success the second time, given that we had a success the first time, is now 5/9, and the failure is 4/9. So notice each time we draw a ball, what's going to happen to the denominator? Well, it's going to go down by 1, right? So it goes down by 1 each time because we've removed a ball, right? So we're choosing from a total number of balls that's decreasing 1 each time. Now the numerator from the previous time, well, one's going to go down and one's going to go up. I mean not going to go up, one's going to stay the same. So one of the numbers so for example, let's look, say we got a success, and then the next time, well, the first time we have 6 black and 4 red, so probability of success is 6/10, failure 4/10. Well, the next time, let's look at the top. We know the denominator is going down to 9. Well, since we got a success, the 6 is going to go down to 5, but the 4 is going to stay the same because we still have 4 reds. On the other hand, if we draw a failure, we draw a red ball, the number of red balls goes down. So it's the 4 that decreases to 3, but it's the 6 that stays the same, and the denominator definitely goes down by 1. And this continues through the whole table. So some interesting numbers that we might want to know are not only capital N and capital M, but we might want to know M is 6, but then we want to go down 5, 4, 3. Subtract M 1 from that each time. So M, M minus 1, M minus 2, and M minus 3. In fact, those 4 things are what we get for the denominator. I'm sorry, that if I did that for N, that would be the denominator. So N is 10, then subtract 1 is get 9, N minus 2 is 8, N minus 3 is 7. And so the denominator is N times N minus 1 times N minus 2 times N minus 3, or in other words, 10 times 9 times 8 times 7, which is 5,040 in this example. By the way, does that look familiar? 4 numbers that we're multiplying together, each one goes down by 1. Well, isn't that just 10 permute 4? Capital N permute little n? That's the denominator. Okay? Some other things that we're being interested in is, for example, along the top path, it's the M's that go down, or the number, not M, but the number of black balls, the number of successful items goes down. So capital M starts out at 6, then capital M minus 1 is 5, then M minus 2 is 4, and 3, and those are the numerators on the top, 6, 5, 4, 3. And so, of course, we're multiplying 6 times 5 times 4 times 3, and that gives you the pink numerator there. M times M minus 1 times M minus 2 times M minus 3 is, well, that works out to be 360. So that's 360 over 5,040. A lot of these things, actually all of them, will reduce a little bit. But that's what it is in unreduced fraction form. All right, now let's look at the next path. Success, 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 failure. Well, look at the numerators are going down 6, 5, 4 for the number of successful draws, and then the next one is 4, which is the number of bad draws, which hasn't decreased. So notice what we're doing is for the numerator there, we're multiplying m times m minus 1 times m minus 2, and then we're multiplying by n minus m, capital N minus capital M, which is 4, which is the number of non-black balls, in this case red ones. So multiply, so in this case we're multiplying 6 times 5 times 4 times 4, and so that turns out to be 480. So that's the numerator there. Now what's really cool about the way this turns out is all of the ones that are in orange turn out to be the same numerator. Look at them. What happens? They have, in every case, we're going to get 3 successes. Okay? So that meant along the way, somewhere along the way, our numerator went 6 and then 5 and 4 in some combination, and we got 1 failure, which is 4 for the numerator there. So in some combination or another, these are all there, and so we get 6 times 5 times 4, and then we also have times 4. So every one of those turns out to be the same thing. Turns out to be m times m minus 1 times m minus 2 times, that's sort of for the green ones, and then for the black part, somewhere along the line, you get an n, capital N minus m, and you multiply all those together, and that's your numerator. And of course, once again, just as in the binomial, we have n choose little n choose one of those. In this case, that makes 4 of those. Now for the black ones, all the black ones have the same numerator. And they're the ones where we have 2 successes and 2 failures. And of course, there are little n choose 2 of those. 4 choose 2 is actually 6, so there's 6 of those. And if you look, since the successes are twice and the failures are twice, we start with the total number of successes and total number of failures, and both go down by 1, multiplying those together. So, in other words, what I mean is, you have m times m minus 1, and you're going to see those two as green numerators somewhere along the path, and you have m minus capital N minus capital M, and capital N minus M minus 1 are the 2 black numerators that you're going to see along the way. Multiply all those together, you get, in this case, 360, and that's the numerator for all those. For the brown ones, all those are the ones that have 1 success, and so they'll have 1 of the green probabilities along the line, and it will definitely have a numerator of 6 because you're drawing 1 of those 6 successful ones. All the others will be black, and so they start out with well, in this case 4 capital N minus capital M, and then they go down by 1. So all of those have numerator capital M times capital N minus capital M times N minus M minus 1 times N minus M minus 2, and that turns out to be, so in other words, in this case, that's a 6 times a 4 times a 3 times a 6 times a 4 times a 3 times a 2, and that turns out to be 360, and that's for all of those, and there are 6 of those. I'm sorry. No, that was the brown ones. It's 144. So M is 6. Then you got N minus M. That's your 4. So these go 4, 3, 2. So 6 times 4, 3, 2, and that's 144. And this brown one, the one at the bottom, the blue stuff really doesn't come into play. It's only the black numbers here. N minus M is 4. Then it goes down 1 to 3, 2, 1. So the numerators are 4, 3, 2, 1. Now, by the way, it's possible that if you run out of a certain number of balls, then they could be 0 from there on out, and a thing disappears here on us. Okay, so this is what the table looks like, and we get this here, and there's a decimal approximation. So what do we have here? If you look, this looks like a permutation, this looks like a permutation, and this one looks like a permutation. Let's see, there's the n minus m's, and you have how many of those? Well, you have x of those factors that start with n minus m and work their way down. How about the n minus m parts? I'm sorry, this is all the n minus m parts, and these start 0, 1, 2, 3. So there's 4 of those there, which is x, what's n minus x. So there are n minus x of those. Okay, what about down here? Let's look at this one here too. We got m and m minus 1, so there's 2 of those, n minus m and n minus m minus 1. So there's these first, well, not the 6, but these 2 right here are a permutation, and these 2 are a permutation. There's a permutation in the bottom, and this 4 and this 6 and this 4, and if we put 1s outside the others, those are a combination. So there's the hypergeometric distribution, this example. Notice the graph is a little different. Remember when we did it with the same setup completely, but it was with replacement, then these 2 bars here were the same. These 2 are a lot closer in size to these 2, and so we got a little bit of different distribution. Now, so what have we seen? We've seen that the denominator is capital N times capital N minus 1, n minus 2, all the way down to n minus little n. So that's n permute n. Capital N permute lowercase n. The coefficient out front was exactly the same one that we had in the binomial theorem. So that was little n choose x. I called it x or k before, same thing. Then these others are permutations too. Capital M permute x. Those were basically all of the, let's see which color. They were the green ones. So those are all the green numerators. And then the capital N minus m permute little n minus x, those were all of the black numerators. And so we multiply those together to get the numerator here, multiply all 3 of those parts. Now, I'm going to rewrite these in factorial notation. I'm going to show you something that's kind of interesting, that we can rewrite this a little bit different way. I'm not really sure if it's completely simplifying it, but perhaps it is. N choose x, remember, is n factorial over n minus x factorial times x factorial. M choose x is m factorial over n permute x is m factorial over m minus x factorial. And similarly for the others. Now I'm going to take the 3 parts of that first one and put them inside the other 3 where they could go. So I'm going to take this, I've kind of colored them so maybe you can see a little bit easier. So take this x factorial and put it in the denominator of this first one here. I took the red factorial here, n minus x factorial, and stuck it in the denominator of this last thing in the numerator here. Now this is an n factorial on the top, could be rewritten as a 1 over n factorial in the denominator, so that n factorial could go in the denominator of this one on the bottom. And what's kind of cool about that is that it turns out to be exactly what you need when you break it up that way to make each of these just a combination or a binomial coefficient. So this first one is m choose x, the second one is n minus m choose n minus x, and the bottom one is n choose n, uppercase n choose lowercase n. And so usually you'll see this formula written that way, that last one, although the way we kind of derived it, the formula at the top was a more natural way of doing it. But of course we can use this using the built-in combination finder binomial coefficient in choose r command in our calculator if we need to. Okay, continuing on. So we've seen the probability density function, the PDF, for a hypergeometric is m choose x times n minus m choose little n minus x over capital N choose little n. it turns out that the expected value of x, without getting into proof of this, it's little n times capital M over capital N. And notice capital M over capital N is what we're sometimes calling P. That's the probability of success the first time. And in fact, that's exactly the same mean, when you write it that way, NP, as the binomial distribution. So that's kind of interesting. It's a slight variation on the binomial, but it turns out that if you write it that way, N times P is still the mean. And if you remember, the variance on the binomial distribution, we didn't prove it, but I stated it, was N times P times Q, and that's the same thing here times this factor right here, capital N minus little m, N, over capital N minus 1. And sometimes this factor right here is called a correction. It's a correction for a finite sample size correction. When you have a finite sample size, you have to be careful that you're drawing from. It's going to change the probability every time. So that's really a hypergeometric situation. If your sample size is infinite, or even if it's, well, if it's infinite, then the probability of success each time is the same. And so then we're in a binomial situation. And sometimes it turns out that the bigger this capital N gets, it turns out that the less difference there is whenever we change one item. Okay, so when I only had 10 items, changing one, once we pulled say a black ball out, that drastically changed the probability. But if I had a trillion items, pulling one ball out changes the probability very, very little. So what happens is, if the N gets really large, this hypergeometric's really close to just a regular old binomial. So if we look there, we can look at it a little bit again. The P, of course, is big M over big N, and of course Q is 1 minus that. But if we rewrite it that way, we get those things. So there gives us a quick look at the hypergeometric. All right, here we go. So we're talking about a hypergeometric distribution versus a binomial distribution. Okay, so a binomial distribution, we know the sample size is n. Hypergeometric, same deal. Again, one way we could think about it is choosing from capital N, total number of items, and capital M is the initial number of successes, and we're trying to get the unknown number of successes. In that case, they're both the same. But a binomial is done with replacement, and a hypergeometric is done without replacement. That's the big difference. So what happens here, if you do it with replacement, it's a binomial distribution because the probability of success is constant. That P is N over M, and it stays the same. We've got independent trials. The probability is the same every time. But if we do it without replacement, the conditional probabilities of a success is going to vary depending on what happened before. And so that's dependent probabilities there. So that's really the main difference, is a binomial is done with replacement so that we have probability of success is the same every time. Hypergeometric is done without replacement, so the conditional probabilities of a success vary from time to time. Otherwise, they're basically set up the same. Okay, that gives us a quick look at hypergeometric.